Let's take a look at question 3 on the 2023 AP free response exam. So this question is looking at this chemical equation between calcium carbonate and HCl and these products. And we're being asked to first write a balanced net-ionic equation for the reaction. So as a reminder, when we're doing net-ionic equations, when you have aqueous compounds, that means they actually dissolved in water. So this HCl and calcium chloride, we should be writing them in their ionic form or as ions, whereas all the solids, liquids, and gases, they don't break apart. They will stay as a compound. So I'm going to make a little note above the reaction and then we'll fix it when we do our final answer. But what we're going to say is that the 2HCl becomes 2H pluses and 2 chlorides. Don't forget the coefficient, that's important. On the product side, the calcium chloride becomes calcium 2 plus, and again, 2 chloride. And so what we're going to do is we're going to look to see that the chloride, 2 chlorides on the left, 2 chlorides on the right, these are going to be taken out of my net-ionic equation because they're spectator ions. So they did not change form from the reactants to products. They didn't really change. So they're just spectating the reaction. So what I'm going to do now is write down my overall, what I'm left over with, and that would be calcium carbonate, solid. We'll put the states here. 2H plus ions, aqueous. Products are calcium ion, aqueous. The chloride was canceled out, CO2 gas, and H2O liquid. All right, that's how we do question 3A. In the next question, in number 3, we're looking at an experiment, factors that affect the rate of reaction. So there's a data table here that looks at varying concentrations of HCl and then also particle size of CaCO3 solid. So we're mixing a couple different factors here, and just as a reminder before we look into this data, in general, remember that as the concentration increases, the rate will also increase. And we do see that in this trend. For example, when I have 1 mole per liter of the acid in a fine powder, 67 seconds. And then when I have 3 moles per liter of the acid in the fine powder, 22 seconds. So the reaction time got faster, which means the rate went up. In addition, particle size also is a factor. Particle size, this actually has to do with surface area. And in general, what happens is as the surface area increases, the rate of reaction also increases because you have more surfaces of that molecule or that compound available to collide. And again, we see that here. The fine powder takes 67 seconds to react, so a quicker reaction time, that means a higher rate. And then the small chunks of that powder at the same concentration took a little longer, right, at 112 seconds. So in general, those are our trends. Now, in terms of the concentration, there can be some exceptions, such as if you have a rate order of 0, but we'll look at that after. I believe there's a question on that. So let's look at this question. It says in trial 5 here, there seems to be inconsistent data. So explain why. Well, a couple things here. Notice that my eye goes to this. The small chunks took 227 seconds to react, whereas the large chunk took less time, 114 seconds. That's not what we expect, because if we look up here, the small chunks should be faster, right? So one kind of error I notice is that the small chunks, they have a greater surface area. So as a result, the small chunk should have reacted faster. Faster than the large. And then there's a second thing I also see here. Maybe I won't write this one down, but it's another thing. I'm looking at the answer key. It looks like you can talk about either one. So the second kind of error is that in trial 5, I am using 3 moles per liter of HCl. And in trial 2, which is like the relatable trial, I'm using 1 moles per liter HCl. And this one's the chunks were consistent, so that's my control variable there. So really, if I look at these reaction times, this is going to be based on the concentration. The 3 moles per liter, this should be faster because it's more concentrated. So there's more molecules of HCl available to collide with the other reactant, calcium carbonate. So again, this should be a smaller number or a faster reaction time compared to the lower concentration. So you can either talk about here the chunks, small chunk versus large chunk, or you can talk about the concentration and why that result is not expected. And then based on this question, I think this is kind of a follow-up. So based on the reaction conditions and collisions that occur between particles, explain the reason for the difference in reaction times for trial 2 and 3. Okay, so again, we kind of talked about that. So trial 2 and 3 is the same concentration, but we see that the format of the solid, of the calcium carbonate, it's a large chunk versus small chunk. So what you have to say for this is that we just have to, and again, we look at, it takes longer for the large chunk to dissolve or to react with HCl. So we have to just talk about the fact that surface area is the factor here at play, right? So let's go down here and we're gonna say that in trial 2 is the small chunks. If you forget, we'll make a little note. This is the small chunks, and then this one was the large chunks. So it makes sense that the small chunks react faster than large because the small chunks have a greater surface area, so they have more faces or more surfaces to collide with the HCl. So small chunks react faster than large chunks due to greater surface area, meaning, and we have to use the word collisions because that's in this question. More collisions can occur with the HCl. Okay, let's do one more before I pause and then do the next part. So it says here the student claims that the reaction rate is 0 order with respect to HCl. Do you agree or disagree with this claim? And then justify your answer using the data. So just as a reminder, rate equals the K constant times the concentration of reactants raised to some sort of exponent. So a 0 order means that this exponent is 0. And what that would mean is no matter what concentration this was, you remember that anything raised to the power of 0 gives you 1, right? So this whole term here, this whole term would equal 1. And so in other words, if it was 0 order, the concentration of HCl would have no impact on the rate. Well, that's not true because we can see from our data table back up here, okay, this is a bit messy. Let me just clean this up a little bit. You can see from this data table that when you have 1 moles per liter at the fine powder, so what, let's look at this when this the particle size is constant. So when you have 1 moles per liter, it was 67 seconds. When you have 3 moles per liter, it was 22 seconds. I can see that the time of reaction shortened, or in other words, the rate went up when I increased the concentration. So HCl, it cannot be 0 order because, so we're gonna say disagree. And that's because HCl, when I increased the concentration, was increased from 1 moles per liter to 3 moles per liter, the time of reaction decreased, which means the rate increased. Remember that time and rate, it's a little confusing, but they're inversely proportional. So if I've got a low reaction time, like a small number for seconds, that means it's a faster rate because that means it changed faster, right? Change in quantity over change in time. Okay, I'm gonna pause it here and I'll do the next part of question 3 in the next